Good morning. Very good morning to all kids. I am going to teach you today about nautical science topic, that is rising and setting of celestial body. We are all aware that there are millions of celestial bodies which are around the earth in the celestial sphere. Out of that, we are curious about using the main celestial bodies, which we call it the sun, the moon, and planets Saturn, Venus, Mars, Jupiter, and also around 57 navigable stars. We have seen in our previous topic about the celestial sphere. Now let us proceed towards learning about rising and setting of celestial bodies. Now if you look at it, as I mentioned, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and they are utilized for navigation purpose. We have seen, or we are aware, that Earth rotates on its axis from west to east. Now if you see the picture, axis is also drawn from North Pole to South Pole, and Earth is rotating from west to east. And this causes west to east rotation, and it is faster near the equator and slower near the pole. It is also indicated on the slide. This rotation is said to be the product of gravitational force and also angular momentum between the planets. This Earth rotation on its axis from west to east, it causes for us to believe that other celestial bodies are rotating from east to west. Actually, the sun stays in its position at the center of our solar system. It does not rise or set, but it appears to rise and also set because of Earth rotation on its axis. It makes one complete turn every 24 hours. As Earth rotates, different locations on the Earth pass through the sunlight. The animation which I am going to show for your better understanding is on the next slide. There you would find out how it looks for every hour. If you see the animation slide, here Earth portion is getting lit by the sunlight, and also the darkness is also seen. The Earth is continuously rotating from west to east. Because of that, the sun is appeared to rise from east to west. The rotation of the Earth makes us to believe the sun rises in the east during the day and sets in the west. And this particular animation which you are seeing it would put you exactly to understand the part of the world which have the sunlight, the other part which have the darkness. As your town in your country turns towards the sun and begins to enter its light, the sun seems to be rising in the east. As your town begins to leave the sunshine and enter darkness, it appears to set in the west. It is very clear from this animation, I hope. All celestial bodies, gentlemen, appear to describe an east-west motion around the earth each day. They appear to move along a circular path around the celestial pole. Thus, a celestial body appears to rise in the east and move westward, gaining altitude until it is on the observer's meridian, which is also termed in celestial equinoctial system and horizon system, which is termed as prime vertical circle on its transit. And then the celestial body moves westward, decreasing its altitude till it sets over the western horizon. Gentlemen, you need to understand, when the sun is rising in the east, the altitude will be zero. As it moving towards the west, from east to west, still it comes over my horizon or over my head, which is called zenith. That is, the maximum altitude will be reached. And thereafter altitude decreases and sun moves towards the west and sets finally in the west. Hence, for a stationary observer, interval between the rising and transition over an observer's meridian of a celestial body is equal to the interval between transition over the observer's meridian to setting of the celestial body. Provided for that day, the celestial body's declination remains almost the same. When you to have an observer on the North Pole. Over the North Pole, imagine you have transited across the globe and reached over the North Pole. For him, the zenith is exactly above the North Pole. It coincides with the celestial North Pole. His rational horizon, which is at 90 degrees from the North Pole, would be also coinciding with celestial equinoctial or the equator or celestial equator. A celestial body with a zero declination would appear to the observer to move along his rational horizon. That is, it is rising in the east, move along the celestial equator and completing an entire circle in exactly the same period as the Earth completes a rotation in 24 hours to 360 degrees. Now let us see the condition where the observer again with the North Pole. But here the celestial body is not having zero declination but have northerly declination. It would appear for the observer for the celestial body to move along a circle maintaining a constant altitude equal to its declination. And it would remain above the rational horizon of him, in this case, the celestial equator at all times. Celestial body with a south declination would always remain below the rational horizon for the observer at the North Pole. As we know, it is 90 degrees from North Pole to the celestial equator. And the celestial body with a southern declination would not be visible to him, to the observer at all. Now let us take an observer on the equator. Here, the rational horizon would be the plane of Earth axis. The equinoctial and all declination circle will be bisected at right angles by his rational horizon. That is to be understood. The rational horizon, which is at 90 degrees from observer's zenith, would bisect the equinoctial. All celestial body, whether having northerly declination or southerly declination or even zero declination, will therefore remain above the horizon for exactly half the day and below the horizon for remaining half the day. All celestial body hence will rise and set perpendicular to the horizon. This is a very rare case, especially when an observer is on the equator. You would experience this. Now let us take observer in the north latitude. He is neither on the equator nor at the pole, but he is between the pole and the equator, but in the northern hemisphere. The rational horizon will bisect the equinoctial at its east and west point. A celestial body with a zero declination would therefore be above the horizon for exactly half the day and below the horizon for the other half. The altitude of the pole is equal to the latitude of the observer. Here we need to understand. I would like to draw a diagram if required by understanding this. Gentlemen, if we draw a rational horizon and name it as celestial north and celestial south, and if you have the horizon system, prime vertical drawn and the principal vertical circle drawn. Now you name it east and west. Now I have an observer in this case who is on the northern hemisphere. I need to look at it. So where would be the zenith? Zenith is the overhead of the observer. He is already in the northern hemisphere. Then where would be the celestial equinoctial? Let us see, it would be south of him. So the cube which is intersecting the principal vertical circle would be south of the zenith. We know that celestial pole is 90 degrees from the equator. And in this case, since the observer is on the northern hemisphere, he would be having the elevated pole of the North Pole. If you draw a line to the rational horizon and this particular diagram, the pole would be appearing closer to the zenith. The P is the elevated North Pole. The distance between Z to P and P to direction north is 90 degrees. And we also know that Q to Z We know Z to N is also 90 degree. Hence, this distance is equal to this distance, which is nothing but latitude. That is what explained in the slide here. As the observer latitude increases, the elevated pole, which I have shown in the previous diagram, it would move towards the zenith. The angle at which the equinoctial intersect is rational horizon will reduce. Therefore, major part of the declination circle of celestial body with the northern declination, same name as the observer's latitude, in this case north latitude, would lie above the horizon and smaller arc below the horizon. So, body with the northern declination would be available or visible for longer duration during the day. And it rises and sets northward of its east-west point. I would like to make it clear, it is for the body who has got or which has got north declination would rise above his east and set above his west. And it is vice versa. With the southern declination, body would rise south of the equinoctial east point and set south of the equinoctial west point. Declination circle of celestial body with a southerly declination opposite observer's latitude, as I mentioned just now, will lie with a major arc of the celestial circle below the horizon and a minor arc above them. What does it translate? Such celestial body would therefore remain above the horizon only for smaller part of the day. They would appear to rise and set, as I mentioned a few seconds back, wherein southward of the observer's east and west point respectively. If the south declination of celestial body is large enough, if it is more than the latitude, the declination circle would lie entirely below the rational horizon and the celestial body would not be visible during any part of the day to the observer who is in the northern hemisphere or having north latitude. There is a period of time a celestial body would remain above the horizon during a day, depends on observer's latitude as well as celestial body's declination. We are aware the main planet which we are looking at, interested, is Sun. Sun is above the horizon during the day and below the horizon during the night. That is why we have day and night period. We are also aware, or you need to be fully aware, the declination of Sun maximum it reaches around 23.5 degrees north and 23.5 degrees south. When the Sun's declination is north, as I mentioned a few slides back, for an observer with the north latitude, Sun will remain above his rational horizon for more than 12 hours. The reason is, for an observer who has got a north latitude, Sun declination also north. The major arc of the celestial declination circle would appear for longer duration. That is the reason. And for observers with the south latitude, the Sun therefore would remain for lesser than 12 hours. This translates into larger part of the day and lesser period of the day also at various parts of our globe. The north hemisphere will have longer day and shorter night, south hemisphere shorter day and longer night. If the observer latitude and the Sun's declination of the same name, I would like to give an indication here with the equation. If the observer's latitude and Sun's declination is equal to or greater than 90 degrees, the Sun would be circumpolar. What is this word circumpolar? In fact, all celestial bodies are circumpolar. Circumpolar is nothing but all celestial bodies are going around the pole. It appears to go around the pole. They are circumpolar. But because of the position of the observer on the Earth's surface, we have taken only few bodies which are called as circumpolar. For a circumpolar body, let us see little more details. As I mentioned, here observer's latitude and Sun's declination, when we add up, it should be equal to 90 degrees or more. Then we term it as circumpolar bodies. When the Sun is at maximum 23 63.5 degree of north designated. Observer latitude above 66.5 degree north would experience this phenomenon known as midnight sun. That's why, gentlemen, Norway is called midnight sun. The latitude of that region is higher than 60 degree north. At this time, observer at latitude above 66 degrees south, let us look at southern hemisphere, would have continuous night as the sun would always remain below the observer's horizon of the observer who is in southern hemisphere. Now let us come to the next topic, which is related to this rising and setting of heavenly body. But it is related to the sun. Twilight. Twilight is the light received from the sun when the sun is below the horizon. It is before the sunrise in the morning and after sunset in the evening. When the sun is below the horizon, it illuminates the upper layer of the atmosphere and part of light is further reflected and scattered in various directions over the earth. This scattered light illuminates the earth's surface for some time. Gentlemen, you might have seen when you see the sunrise in the morning, month before that, the sunlight is available, but sun is not seen. That duration between the total darkness, where the light breaks out, but sun appears over the horizon. This period is called twilight in the morning. Similarly, if you look at it in the evening, sun sets, thereafter sunlight is still visible or available. It is not fully dark. This period, until it becomes fully dark, is called twilight. Now, twilight is completely ceases in the evening when the sun is 18 degrees vertically below the horizon, and after that, total darkness appears. What is this 18 degrees? Let us look at it. Gentlemen, when the rational horizon, as we have drawn here, the rational horizon in the previous diagram, from the rational horizon, if the sun is below 18 degrees, above the rational horizon, we call it altitude. Below it, if it goes, when the sun comes over there, the twilight breaks out. As it rises from 18 degrees to 17, 16, 15, like that, when it comes to 12 degrees, the same twilight is termed as nautical twilight. So between 18 to 12 degrees, it is called astronomical twilight, and between 12 degrees to 6 degrees, when the sun is available below the horizon, it is called nautical twilight. And between 6 degrees till the sun appears at the rational horizon, that is 6 degrees to 0 degree, it is called civil twilight. Let us understand all three terms once again. What is astronomical twilight? It is sun is 18 degrees below the rational horizon and it keeps rising. It comes up to 12 degrees. During this period, sunlight will be visible, but horizon will not be clear. However, entire celestial sphere will be illuminated with our stars and planets as we see in the total darkness. But we cannot make use of them for sight, astro sight for position fixing. Now let us come to the next term, nautical twilight. It is specifically called nautical twilight. Reason being, now from 12 degrees, when the sun rises up to 6 degrees below the horizon, during this period, sunlight would be enough to illuminate the horizon. Also, at this juncture, you would see all stars and planets which are bright enough for a human to observe. This period is used for astrosight. Between 6 degrees to 0 degree till the sun reaches the rational horizon, the sunlight will be so powerful, stars and planets which were appearing so far would disappear. But the horizon will be well lit, we may not be able to use it. That's why it is called civil twilight. When sun breaks the rational horizon at 0 degree, thereafter rising, we say that theoretical sunrises occur. Similar pattern at sunset, when the sun is setting, again 3 stages of twilight occur. Here, first one will be civil twilight, between rational horizon till 6 degrees below the rational horizon, civil twilight. And thereafter it is called nautical twilight in the evening, which is from 6 degree below the rational horizon to 12 degree below the rational horizon. This period is again called nautical twilight because we may make use of this period for astroscience. Thereafter, once again, the astronomical twilight occurs between 12 degree and 18 degree below the rational horizon of the sun. So this, we know that twilight is very important for astronavigation. At sunrise, all three stages commences when the sun's upper limb disappears over the visible horizon. That is, the twilight started when it was 18 degree below the rational horizon. Moment the upper limb of the sun appears over the rational horizon or visible horizon, when it is visible, the twilight vanishes. Whereas in the evening, it is the other way around. Each twilight lasts until visible sunrise, it is upper limb is appearing. Now, with the diagram, I have explained that. If you look at the diagram, the angle of 18 degree, 12 degree, and 6 degree coinciding with all three terms of twilight: astronomical, nautical, and civil. Twilight in the sunrise period as well as sunset period is explained. This one, the twilight as well as the sunrise. I will be dealing in the part 2 of this presentation how it is important for us. We need to understand what is the spherical triangle which is playing the role, the elevated pole P and the zenith and the heavenly body X, the position in the celestial sphere which is going to determine the spherical triangle established between three angles of it. We will be seeing it in the part 2. Twilight period to be lasting long. Now for a continuous twilight, I would like to mention it, for continuous twilight throughout the night, there will be places on the earth's surface where the sunlight will be visible throughout the night. Sun has set, but that period is called continuous twilight throughout the night. Here, equation wise, if we have to put it, observer's latitude and sun's declination is plus 18 degree. If you add up the twilight, if it is equal to or greater than 90 degree, the sun will not go below the twilight belt at all. It would remain above 18 degree. However, since the latitude and declination when you add up, if it is less than or equal to 90 degree, sunset will occur or sun will rise also. But it is not moving below the 18 degree belt. So you have throughout the night twilight. Now let us look at theoretical sunrise and sunset. There is a difference between visible sunrise and sunset. At the visible horizon, which your eye can see from the raised platform of your bridge from the sea level to certain distance only. That is the visible horizon what you see. The sun we can see only when it appears at the visible horizon. Whereas the sun is moving and we need to account for the rational horizon from our zenith, which is at 90 degree. When the sun is at the rational horizon, the altitude of the sun would be 0. So from us to the sun, the zenith distance is 90 degree. I will touch upon it with the P and the triangle in the part 2 so that you understand the calculation which are used for our navigation purpose. Now diagrammatically that has been explained to you. Here a point to be understood. We have a phenomenon called refraction which you have already learned. Because of the refraction, when the sun is below the visible horizon, it appears as if it is above. Because the light which is transmitted from the sun, when it reaches the observer, it gets refracted and pushes the image upward. That is what I would like you to remember it. When the sun is at the theoretical rising, that is at the rational horizon, for us sun would have already been visible because of this particular phenomenon called refraction, which has been shown. It is the same case when the sun is being seen visibly setting. Actually, sun has traversed towards much below that angle. Now, if we see, this picture will be very clear. Apparent position of the sun has been indicated, and also actual position of the sun. The difference in angle, because because of the atmospheric layer, the refraction which is occurring for the observer to show. This particular dimension, how much degree or how many minutes it is refraction is making us. Generally, if you look at it, it is around 50 minutes, almost about 0.8 degree. The sun, when it is appearing above the visible horizon, generally the term what we say is when it is 1 semi-diameter above the visible horizon, the sun. That means this is the time the sun is just at the rational horizon. So, true sun, when it is appearing at the rational horizon, you would be seeing because of refraction, the sun has appeared above the visible horizon. That's why we need to take sun appearing at this time from the ship general compass for correcting the compass error. With this, gentlemen, I am sure you would have understood the theoretical sunrise and sunset, and particularly and also the rising and setting of celestial bodies. Let us see in the next part how we make use of it for navigation, theoretical sunrise and sunsets, with calculations involved in that. Thank you.